My name is Calvin Murdock, and this summer I worked with Professor Pless on Inferring Cloud cover from Webcam Images. And the first question you might ask could be, why bother? So clouds are extremely important for understanding and predicting weather and climate, but the mechanism by which they form and propagate in the atmosphere is very difficult and involves many external factors that can be difficult to measure. Luckily, we have a system of satellites which can measure clouds directly by capturing image sequences like this. But the question is, what happens when these sequences are suddenly unavailable? So are there any other measurements that we could use to measure clouds? And if so, how can we do that? So currently, the archive of many outdoor scenes consists of 130 million images from over 17,000 stationary outdoor cameras, many of which are geolocated. So we know the exact position of the camera, and we have consistently updating images from those cameras. For the purposes of simplicity and my work this summer with limited time, we assume that instead of using the images directly, we assume we can quantify exactly the cloud cover at the pixel corresponding to the location of the webcam. So for example, instead of using the images, we can say that if there is a satellite image of the United States, for example, we know the pixels at Banks Wharf and the boarding school are to the left, but we don't know the clouds in between there. So basically, the question simplifies to, given these samples of known pixel intensities, how can we infer the corresponding satellite image sequence? So this is basically an interpolation problem. So we have these sparse sets of measurements of a satellite image sequence, and then we're going to try to figure out how we can use information to figure out what's in between those locations. And luckily, clouds have relatively predictable shapes and movement patterns, so we can use math, hopefully, to help us figure this problem out. The first step of this process is learning the spatial statistics of cloud distributions, and this is done with principal component analysis. Secondly, we can learn the temporal statistics of cloud motion, and we did this with dynamic textures. And thirdly, we need to drive this model towards known measurements from the webcams, or in this case, the ideal measurements that we get from the satellite images themselves. And this is done with a Kalman filter. And then finally, I will give results on how this process works on an actual image sequence of satellite images. First off, principal component analysis is a way to project the high-dimensional pixel data onto a much lower dimensional orthonormal basis with maximum variance. So it's able to best reconstruct the maximum number of images that we could have in our sequence. Then we can approximately reconstruct the images from a linear combination of these components. For example, if we have a sequence of images from any camera, for example, in this case we're using a webcam, not a satellite image sequence, which we'll be using eventually. But we're able to form a matrix by using these images as the column vectors in the matrix. And then principal component analysis is a way of approximately factoring this matrix into two smaller matrices, the first of which contains the basis vectors, or principal components, and the second matrix contains the coefficients corresponding to the weights that we give in the linear combination of the principal components that approximately reconstructs the original images. So basically, if you want to reconstruct the first image in the sequence, which is the first column in the far left matrix, we can take the first column of the matrix, of the coefficient matrix, and then multiply them by the corresponding principal components, and then add them together. So when we tried to perform this on a satellite image sequence, these are the first 6 principal components. And then, again, we can take a linear combination of these images to produce a prediction of what the satellite image looks like. And as you can see, when you run the process on an entire image that covers much physical space. In this case, we're doing it over China, like the eastern side of China and Japan. The results are very blurry, and there's not a lot of detail. And you can't really say where exactly the clouds are in that image. So our way of addressing this problem is using a Voronoi partition to group pixels in the satellite image with the nearest measurement site. And then we can compute piece data locally and independently for each of the regions. And this should allow there to be less variation within the smaller regions. So we should hopefully be able to better reconstruct the target satellite image. And when we do this, these are the first 6 principal components of the individual regions. And when we reconstruct an image, you can see that there's a lot more detail, and we can actually figure out where exactly the clouds are in the image. Okay. So now that we have a way of statistically modeling how clouds are distributed spatially, we still need a way to determine how these coefficients and thus how the images themselves change over time. And this was done with an autoregressive model which predicts a multivariate signal from prior values. So for our case, it's going to predict future images solely from their prior PCA coefficients. So from the previous example, these were the coefficients in time of our previous image sequence. And as you can see, there are some pretty obvious periodic behavior and relationships between the two coefficients. So intuitively, we can guess that there must be some way of predicting how these will continue in the future. But as the number of principal components increases, and if the motion that we're trying to model is much more complex, this can be a very difficult process. So basically, dynamic textures is a mathematical way to predict this kind of regular behavior in a more robust form. For example, if we have a first-order model, it takes one set of coefficients or one image that we know exactly, and then from that image, we can predict future images, and then from those future images, we can predict even future images, and we can continue this for as long as we need to construct the sequence. And this idea can be generalized to higher order models, which, for example, take 2 sets of previous coefficients that are known exactly, and then using both of them, we can have a better idea of how to predict the next images. And again, this can continue for as long as necessary. So we have a way of giving an approximate total prediction for the next frame with dynamic textures. Remember, we also have the exact pixel measurement at the location corresponding to the webcam. So now we need a way to figure out how to combine these 2 measurements, because on their own, they're not giving us the most accurate information. So Kalman filter is a way to optimally combine these 2 predictions into a more accurate joint prediction. For example, here is a graph of the pixel intensity at a single measurement site, which is the location of a single webcam in a region that we're trying to find the cloud cover over. The x-axis represents time, and the y-axis represents the value of that pixel. The green line represents the ground truth, or what we actually know, the measurements given by the webcams. And the blue line represents the prediction just from the dynamic textures. And as you can see, the blue line diverges continuously with time, and it becomes even more and more off from the goal, which is the green ground truth line. But when we combine the information from the webcams and the dynamic texture model, we have a much more accurate representation because, as you can see, the red line follows more closely with the green absolute truth. Finally, we can give some results on how this process performed with actual satellite image sequences. Here is an animation. The far left shows the original sequence, or the target images that we're trying to reproduce. And remember, we only know a sparse set of measurements of the pixels in this original sequence. So if you imagine that, let's say, you only know some certain pixels, and you can imagine how difficult it could be to figure out how the clouds are in between those sites. The far right shows the results of just using the dynamic texture model without the Kalman filter. And as you can see, it starts out okay, but as time goes on, we can see that the error is increasing and it's becoming more and more less and less accurate. But in the middle, we show that when we combine the information from the webcams, we can modify this model to more accurately follow what is actually in the original sequence. So you can see, as time goes, you can see that there's a cloud that comes by, and it matches fairly well with the original sequence. Furthermore, we can show a graph that represents the total error averaged over all the pixels in the sequence. So the green line represents the error, the intrinsic error that's associated with PCA reconstruction. Remember, we can't reconstruct all of the images exactly with the limited number of physical components. So this is about as good as we could possibly hope to do. When we use this line represents the ideal dynamic texture. So this is showing a single prediction given that we know all of the previous coefficients exactly. Which is not the case, because if you need to predict further than just one frame, you need to be able to use measurements that we already predicted. And this line shows the results of continually using these predictions and updating them. And as you can see, it diverges significantly from the ideal amount of error, just because we're using predictions to predict more predictions, and the error just grows and grows over time. And then finally, this is the result of using the Calvin filter to kind of rein in the dynamic texture model so that it better agrees with the webcam measurements that we have at those specific pixels. And the error is much better, as you can see. And then we can also show a graph that shows the sample error, or the mean error at just the sample sites that we know the exact pixel measurement of. So instead of averaging the error over all of the pixels in the image, we only average the error over the pixels corresponding to the measurement sites or the locations of the webcams themselves. So as you can see, the green and the teal lines are relatively the same, and the blue, again, diverges consistently over time. But when we use the Calvin filter, you can see that the error is much less, even less than the PCA reconstruction, which is showing that the Calvin filter is working as we expect it to, in order to decrease the error at the measurement sites. In conclusion, we have shown that it is feasible to predict complicated cloud behavior with localized Calvin filter dynamic textures. And luckily, there is still work that can be done in order to achieve more accurate results, especially for extrapolated satellite sequences that go further and further into unknown territory. For future work, we hope to actually use the webcam images, and then hopefully we will be able to potentially extract more useful information than just single pixel intensities at the locations of the webcams. And then finally, I don't know if you noticed earlier on, but there was an issue with consistency between the regions. And this is because we were computing each region independently, which you can imagine is not necessarily a reasonable assumption, because for larger clouds, they could potentially span more than one region. And we want to be able to include all of the information together. And to take advantage of these inter-region relationships, we hope to potentially use a graphical model or Markov random fields. And that is it. Thank you very much.